Hi everybody, this is Mrs. Mancuso. Today's video is going to be about heating and cooling curves. And so if this is my graph, over here it's showing the temperature, which is a measure of the kinetic energy, and this is over time. So if I started off with a solid, my solid could go up in temperature until it reached the melting point. So right here, this would be the melting point of my liquid, or where it becomes a liquid. So here it is a solid, and at this point it's becoming a liquid. And for a solid to change into a liquid, it has to break intermolecular forces of attraction. So the molecules have to actually physically move away from each other. And that's going to require some heat. And then it requires more heat to go up in temperature again. And then the next plateau is when it's changing from a liquid to a gas. So this would be the boiling point. All right, so that is a heating curve if I'm going up, and a cooling curve if instead I would be going down. So let's talk about kinetic energy versus potential energy. So at each of these points when the slope is increasing, my kinetic energy is going up, but my potential energy is staying the same. And here, the kinetic energy stays the same, but if I am going up in heat, my potential energy is going up. So each of the plateaus, the kinetic energy, the temperature remains the same, but the potential goes up. And for each of the slope regions, my kinetic energy is increasing because my temperature is going up, but the potential energy is staying the same. All right, this point right here on the curve, we call this fusion. And if I'm going, so I have a solid and a liquid here because it's changing phases. And if I am going this direction, I'm melting. And if I go this direction, I'm freezing. And then up here, if I go this direction, I'm vaporizing. And if I go this direction, I would be condensing. All right, so this one was freeze going that way, and this one is melting going this way. All right, now this leads us into all of our heat formulas. So heat is not really a measure, like temperature doesn't measure heat. You have to also know the mass. The mass is taken into consideration in a heat formula. So I'm going to grab the reference tables and I'm going to show you where you find your heat formulas. Over here on the back, here we go, heat. And they're all Q. So Q is the value for heat. And there's 3 different formulas you use based on where you are on the graph. So I'm going to go like this. Oops, sorry. Dropped ya. Okay, I'm going to go like this. I'm going to go back to this graph. If I am changing temperature, so if I'm in this region, or this region here, I would use my Q equals MC delta T because the temperature is changing. And C, the value for C for water is 4.18. So where do I get that from? Go back to the reference tables, and on the very front, table B, specific heat of water, 4.18 joules per gram. Okay. If I am in this section of the graph, that first plateau, I am melting or freezing, so I am at the phase change called fusion, so Q equals MHF. The heat of fusion here on the table is equal to 334 for water. So if I am using water and I'm saying how much heat would it take to melt this, I would do Q equals MHF. I would have the mass of the ice and then the 334. And then my other plateau, since this is vaporizing, this is Q equals MHV. So I take my mass, and for water, I multiply it by 2260. All right, so that is how you do heat formulas, and that's how you do heating and cooling curves. Thanks for joining me.